Okay. So now we're on chapter 19. We should be dealing with aldehydes and ketones. Yeah, aldehydes and ketones. The next couple of chapters that we'll be talking about, we'll be dealing mainly with carbonyl compounds. Okay, and generally carbonyl compounds are compound that has a carbon oxygen double bond, functional group in, flanked by different things. Okay, the CO double bond is what we refer to as the carbonyl, and depending on what you have surrounding that CO oxygen double bond, you could have different classes of carbonyl. Now, when an alkyl group or an aryl group is connected to the CO double bond, we refer to that as acyl group. So you'll be hearing me saying that a lot, acyl group. Okay, that's an acyl group. So on this page I have the different kind of carbonyls that we'll probably be talking about throughout the remainder of this semester. An aldehyde is a carbonyl that has hydrogen and an alkyl surrounding the carbon-oxygen double bond. But if the hydrogen is replaced by another alkyl group or aryl group, then it becomes a ketone. If the acyl group, so this is the acyl group, if the acyl group has hydroxyl group connected to it, that's a carboxylic acid. You know that by now. If it's connected to an halide, you know, halogen, bromine, chlorine, iodine, it's called acid halide. Esters, when you have an alkoxide connected to the acyl group. So the acyl group is common to all of them. Now, the chemistry that these groups undergo is as a result of what you have connected to the acyl group. If you look at the aldehyde and the ketone, the acyl group has an alkyl or hydrogen connected to it, which is a poor leaving group. Okay? Because they are poor leaving group, you cannot conduct a substitution reaction on that aldehyde and ketone. The only reaction you can conduct is addition reaction. Okay? So you have a nucleophilic or electrophilic addition reaction. I can't see it very well. Oh my goodness, I should have brought my book. So you cannot have a nucleophilic substitution reaction on those. But if you look at the derivatives of the carboxylic acid, so starting from the carboxylic acid to the derivatives, they have good leaving groups. All right? And that informs the reaction they participate in. So generally, they will participate in nucleophilic acyl substitution reaction. We're going to get to that later on. So in general, for aldehyde and ketone, all you're going to have is a nucleophilic addition reaction. So let's just use generic. If you react this with a nucleophile, the nucleophile is going to add in general. So this could be the same, they could be different. That's why the glasses is good. Can't see that. Oh my goodness. Can't even see what I'm writing. Okay, so then you have the nucleophile. Okay? So the reaction, most of the reaction that the aldehyde and ketone will undergo will be nucleophilic addition reaction. Okay? And we'll talk to that. Yes?
And you said that because they were
because they don't have, so these are poor leaving group. Okay? In fact, there's just one reaction in which hydride act as a leaving group, and that's a what's it called? It's a Cannizzaro reaction, which we're going to talk about, which is useless reaction. But yeah. So, and the alkyl group is also a poor leaving group. Okay. Whereas for the derivatives of the carboxylic acid, all these groups that you have connected to the acyl group can act as a leaving group. Okay. Although for carboxylic acid, this is a poor leaving group, but you can protonate it and make it leave, right? Or convert it to something else that will make it leave. Whereas for the aldehydes and the ketones, you cannot convert them to anything to make them a good leaving group. Okay. All right. So that's the aldehyde functional group and the ketone functional group. How do we name them? So you know the drill, right? We name, we synthesize, and then we react, right? So how do we name them? To name an aldehyde, you're going to change the name of the corresponding alkane. So you find the longest chain in the longest carbon chain in the molecule, and you change the corresponding name of that alkane. You change the E that ends it to Al, so from alkane to alkanal, right? So you change the E that ends the name to Al. The aldehyde functional group is usually at the end of the chain. It cannot be in the middle of the chain. So if you have the carbonyl in the middle of the chain, it's no longer aldehyde, it's already a ketone, right? So therefore that aldehyde carbon has to be numbered carbon number 1. Okay? So let's look at a few examples here. Here you have, so this is the aldehyde functional group, so that's carbon 1, this is carbon 2. So the longest carbon chain there is 2 from ethane, right? So you can call it ethanal. So you change the E to Al, okay? But this acyl group has a common name in acetyl, so you can say acetaldehyde as a common name. Okay, but the IUPAC name will be ethanal. For the second one, you have 1, 2, 3. And what would that be? Propanal. Don't be scared to say it out. Okay. So here you have 1, 2, 3, 4, 5. So you have a methyl group coming off of the longest chain, correct? And then you have an ethyl group coming off of base. Okay? So E comes before M in alphabetical order. So this is going to be 2-ethyl 4-methyl, and then you write the name of the, so it's 5-pentanal. Pentanal. Okay. So if it's a cyclic aldehyde, okay, you're going to add carbaldehyde to the name, so you're calling this carbaldehyde, and then you identify what the cyclic group there is. Okay, so this is a cyclohexane. Carbaldehyde. Okay. For this next example here, we know that this is naphthalene, correct? Okay, that group there is called naphthalene, but your aldehyde functional group here is at position 1 and 2. Okay, so therefore this is going to be 2 naphthalene carbaldehyde. Okay, so that's how to name those.
I have a question.
Hmm?
I have a question.
Yeah,
Why'd you start? Why'd you make the aldehyde number 2?
that's a very good question. So this is the parent chain, the naphthalene, okay? And if you look at this, this is kind of, without the aldehyde functional group, this is like a symmetrical molecule. So how many different carbons do you have in this? It would be, you have 1, 2, 3 carbons, correct? But the counting for the numbering, if you have a substrate of naphthalene, starts from the first carbon after the point of fusion. Okay, so you start numbering it from this carbon. Okay, you're not numbering the aldehyde at all in cyclic ring. You're just calling it carbaldehyde. Okay, what you're numbering is whatever ring it's coming off of.
Right, but you usually make the functional group number 1. That's fine.
Yeah, so but in cyclic you don't make it number 1. That's why you're adding carbaldehyde to the name to show that that aldehyde functional group is connected to a ring. All right, so that's a good question. Make sense? So in a ring, the aldehyde is connected directly to the ring, and whatever position is connected to, for cycloalkane, for example, that position will be number 1 if there's any other alkane in there. But for naphthalene, it's a little bit different. In naphthalene, this carbon that is next to the point of fusion of the 2 rings is numbered carbon number 1. Okay, and this will be carbon number 2. This will be carbon number 1. That will be carbon number 2. Okay, yeah.
So if you don't have a double ringed fusion, like if you just had like say a benzene ring, then that would just be like.
So this is called benzaldehyde. Hold on. Benzaldehyde. Okay, which is the adopted name. But if you want to go by the IUPAC name, this ring is a benzene.
Right.
So it says name the ring and then add carbaldehyde to it. Okay? So by IUPAC, this would be benzene carbaldehyde. Okay? The reason you call it again carbaldehyde is just to indicate that this aldehyde functional group is connected to the ring.
But that would be a position 1 this time, right? And not.
Yeah, so this will be position 1. So substitution on benzene ring, right?
Right.
So if you want to treat it as benzaldehyde, if you have any other thing coming off, now we're digressing a little bit, but that's okay. What will the name of that be? So that will be ortho-bromo-benzaldehyde, if you want to use the common name, or if you want to use the IUPAC name, it will be 2-bromo-benzene carbaldehyde. Okay, because the point of connection here in this case is going to be carbon number 1. For naphthalene, it's different.
Why? Does it matter that they're aromatic? It would be the same if they were just cyclic.
Like what?
So if you have the same molecule as naphthalene, but without the double bonds, it would still be the same.
Well, so naphthalene is a common name. So let's see, what example can I think of on top of my head? I don't know on top of my head what other fused molecule we have. Anthracene, when you have 3 benzene rings fused together, they have their own pattern of numbering. Okay, so
Yeah, but when it's not benzene and just cyclohexanes, you still do the same numbering scheme.
So if there was another one attached to the first.
So if it is a cycloalkane,
if you had two cycloalkanes together, would you still do the numbering thing?
So that is going to be something I'm not going to be giving you, but it's another level of chemistry here. Let's say you have this. Okay, this is a fused ring, right? They have their own pattern of naming, which you've not covered in alkane, in cycloalkane. Okay, so you're now going into maybe terpenes and stuff like that. Okay, so you could have these, you could have, you know, let's see, 1, 2, 3. Right? We're going into another chemistry. Nobody's going to be giving you this at this point. Okay? The common one is the one we'll be giving you. Cyclohexane, you know those, right? Cyclopentane, cyclopropane, cyclobutane, so one ring. For naphthalene, because it's a common reagent, so we'll give that to you. For benzaldehyde, because it's common, we give that to you. For phenol, because it's common, we give that to you. For anthracene, okay, we give that to you for recognition purpose, so that you recognize it. Okay, but they are, so these are heterocycles. Believe it or not, there's another course in heterocyclic chemistry, chemistry of heterocycles, heterocycle chemistry. There you're going to learn how to name heterocycles in their diverse form, okay, and how to make them in their diverse form. All right, but the common one that we're giving you, just stick with that for now. Make sense? Make sense? Okay, good. All right. Okay, I'm going to bring one example from the book in naming before we go to the ketone, and then I'm going to use the same example in ketone. Let's look at this D. Okay, if you look at D, you can see that you have what? You have chiral center. I guess the reason I'm very picky about chirality is because that's my field of specialization. That's a whole other chemistry, asymmetric synthesis. It deals with stereochemistry. So when we draw structure and we ask you to give the name, if there is a stereochemical center, you have to indicate R or S. Don't use Cs and trans. Mark Murray did a bad job using Cs and trans for things like this, because you can use the Cs and trans if you have, you know, let's say, I don't know, what can I even think of? Let's say you have the aldehyde like this. There's a plane of symmetry in that molecule. So if I give you a stereochemistry here, you can use Cs and trans because it doesn't really matter. But by the time you have stereochemical center, like in this case, this is a chiral molecule. Oh, I can't see this very well. Okay? You can, even though the relationship of the methyl to the aldehyde functional group is trans, in the naming you cannot say trans. I know that in the book they said trans this. That is incorrect. Okay? Because this is different from, look at this trans. Let me draw the other trans. So if I make this aldehyde and then this methyl, these are two different compounds, even though the relationship of the methyl to the aldehyde functional group is trans, but they are two different compounds. All right, so that's why you should use R and S. That was why we taught you stereochemistry in chapter 6, I believe, right? Before any naming that has to do with stereochemistry. Okay, so that with that concept, you go into naming. When you see a structure, you recognize a chiral center, you have to show the stereochemistry. If there's a plane of symmetry, fine. Make sense? All right, so if we want to name this, how do we name it? Well, the carbon to which the aldehyde functional group is connected at this point is going to be carbon number 1, because we're going to add carbaldehyde to the end, which takes care of the aldehyde functional group. Make sense? So this is our 1, that's our 2, and then 3, 4, 5, 6. So we know it's a cyclohexane ring, right? A methyl is at position 2, but there is chirality at position 1 and 2. Okay, so to name this, you first have to determine the chirality at 2 and 1. So what is the chirality at 1? So you have 1, 2, 3. So you're going this way, like you're writing an S, but your hydrogen is pointing towards you. So you have to invert that stereochemistry. So even though it looks like an S, it's actually an R. So at position 1 is R, so this point is R. And at position 2, what do you have there? 1, 2, 3. So it's like R, and the hydrogen is behind, so you keep that stereochemistry. So that's R. Okay? So when you want to name this now, that has to reflect in the name. Where did I write it? Let me write it somewhere here. So the name for D here will be 1R, 2R, and then you proceed with every other thing. So 2-methyl, that's all we have, right? Cyclohexane, and then I'm going to, the carbaldehyde doesn't fit in there, that's why I'm writing it down here. Carbaldehyde.
Professor?
Okay.
Could you explain how carbon 2 would have the R configuration?
Okay, so this is our bond. So this bond is our bond number 1 because it's connected to the aldehyde here. This will be bond number 2, okay, and this will be bond number 3. So 1, 2, 3. So it's like you're writing R. You're going clockwise, right? Okay. All right. So, and if you have to look at this, you see that there is complete inversion of stereochemistry in this at this point. So this is what? S, correct? And that will be S. So they are enantiomers. Okay, but from the same molecule, remember, if you have 2 chiral centers, the number of stereoisomers you can get for a molecule that has a chiral center is N, is what? N raised to power 2 or 2 raised to power N? You have to remember that.
What was the question?
If you have a chiral center in a molecule and you're asked to draw all the possible stereoisomers that you can have for that molecule, how do you determine that? How many stereo?
2 to N.
Huh? Is it 2 to N or N to 2?
It's 2 to...
It's 2 raised to power N. Okay? So if you have 1 chiral center, it's going to be 2 raised to power 1. So that means you can have 2 stereoisomers. Those are enantiomers. In this case, you have 2 chiral centers, so N is going to be raised to power 2, right? That means you have 4 stereoisomers that you can get. So that means I can still draw, something like this with the methyl, so with them being cis to each other, right? Have I drawn? Yeah, so we could draw this. You could draw that. And then we asked to name any of those, right? So what's the relationship of these to the first structure there now?
Diastereomer.
They are diastereomer. Because you have inversion of stereochemistry at 1 chiral center, not at both chiral center. Okay? So those are the things you have to review. Okay? It's very important. I just saw that, I said I should bring it up to you guys before we move on to the ketone. We're going to see the same thing for ketone. Oh, by the way, you have common names here that you probably, you want to remember because they're very common. Formaldehyde is the simplest aldehyde you can have. It's from methanol. Methanol is from methane. Acetaldehyde is ethanol. Acrolein is propanol. Okay. Croton aldehyde is 2-butanol. Why is it 2-butanol? Well, your aldehyde is 1, 2, 3, 4. So even if you have double bond in the chain, the aldehyde still take position number 1. Make sense? All right. And then, oh, here's the benzene. Benzaldehyde. You see that? So the IUPAC name is going to be benzene carbaldehyde. Okay? All right, cool. If there's one thing that is guaranteed is that you're going to get naming in anything that you do, right? Quizzes, exams. So. All right. For ketone, how do you name ketones? To name ketones, you replace the E that ends the corresponding alkane name to on. Sounds like it looks like it's written like one, but it's on, right? On. Okay, and then you have to find the longest parent longest chain in the group, and you want to make sure that the first carbon on that chain is nearer to your carbonyl carbon. So let's look at these few examples here. We could start from here. This would be 1, 2, 3. Okay, if you start from here to be 1, 2, 3, but if you start from your right to your left, it will be 1, 2, 3, 4. So you have to start from your left to your right. Okay. So this is going to be what? 1, 2, 3, 4, 5, 6. So it's 3. Hexanon. So you change the A to, so 3 hexanon. If you want to choose the common name, I mean the newer way of naming it, to indicate the functional group, say hexan 3 on, whichever one you prefer. That's fine with me. Okay. Look at the second example. If you go from here, you get 1, 2. If you go from here to your alkene is going to be at position number 2. So you may be tempted to give the alkene priority, but that will be incorrect. Okay? The way the chemistry has been designed is we're going in order of priority of functional groups in the way we're teaching you. So we went from the alkane to alkene to alkyne, alkyl halide, now to these guys. Well, alcohol, and then now to these guys. Okay? So the ketone, the aldehyde will have priority over alkene or alkyne. Okay, if you have a choice between the two, so this carbon is at position 2, the alkene is at position 2, so you give the ketone priority. Make sense? All right. So, but you still have to indicate the position of the double bonds. So in this case, the double bond will now be at position number 4. Okay. So we're going to call this 2. Oh boy, 2. Yeah, you're right. 4 is 6, so it's hexane 2 on. Okay, so the 4 is indicating the locant for the position of the alkene, and the 2 is the position for the ketone. Or if you want to do the newer method, which splits them based on the functional group they are describing, so it will be x4 in 2 on. The 4 is for the in, the 2 is for the on. All right. Now here's an example that wasn't given in the book, but again you have to think broadly, right? Since you're talking about alkene in the naming, you also have to remember the cis trans, right? So let's say you're given a structure like this. It's not going to be enough to just say that, so 1, 2, 3, to just say that you have, 3, what? 1, 2, 3. Okay, well, let's try to name this. Let's just name it. Okay, so if you want to name this now, the name for this will be different from the name. So, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. The name for this guy is going to be different from the name of this guy, correct? So if you're given one structure that has an alkene, remember the cis trans, EZ, in this case it's going to be EZ conformation, right? So don't just limit it to, so because in this example that Mark Murray gave, it's like in condensed form, so you don't have to worry about cis trans, EZ configuration, right? But if we draw it out in skeletal form, you're going to see the EZ, cis trans. Okay, so let's try to name this. 4, 5, 6, 7. So you have a methyl at position what? 4. So it's 4 methyl. Okay. Our double bond is at position 3. So it's 3, and there's nothing else. So 7 heptad. So it's 18. 2 on. But because this is drawn out in skeletal form, we have to indicate the stereochemistry. Well, yeah. So this is going to be largest group here on the same side as this largest group here. It's the same size, right? Z. That'll be the correct name. Okay, whereas that's going to be what? E. Right? And even though, again, it's not stated in, or you don't have an example of that in the book, you should think about everything you've known about naming of alkene. So you could also have a structure that has more than one double bond. Okay? So you have to worry about the stereochemistry at those two positions. Make sense? All right. So there are certain things they just left out deliberately because they feel we've talked about that in 251, so you should know it. All right? Good. So if you have more than one ketone group in your structure, then you introduce dion, trion if it's 3, tetraon if it's 4, and so on and so forth. The same thing with aldehyde, right? So you could have 2 aldehyde functional group at the ends, correct? So that would be dial. Okay? I know it wasn't in the book. Let's. So what would that be? 1, 2, 3, 4, 5. Okay. So it's penta what? Dial. All right. So okay. So now let's look at this example here. This carbon is 1, this is 2, that will be 3, this will be 4, this will be 5, that will be 6. So how would you name that? 2, 2, 4,
Hexadione.
Hexane.
Die.
So why did we have to put the hexane? Remember, it's the E at the end that will change to R, right?
Why is it diol?
Oh, dion. That is still in my head. Thank you. Dion. Thank you. Okay, so dion. All right. Let me write it out clearly. 2, 4, hexane. So we keep the E, put dion.
It's not hexadione.
No, it's not hexadione.
You keep the N and the E.
Pentane dial. Did I say pentadiol?
Yeah, it's
Yeah.
like penta.
Pentane dial. Let me write it out. because it's the E that ends the name that we're changing to al. Now, because we have two consonants together, it's not going to sound very good. So that's why you're leaving it. So pentane dial. Okay. It will be redundant to say 1,5 pentane dial because you know they're terminal anyways, right? So
you don't have to put the 1 and 5 in.
Because they're terminal anyways, right?
Right.
Okay. If it's somewhere in the middle, oh boy, now I'm digressing a lot, right? See, I'm just trying to feed you with all the options you can get out there, which is not in the book, but now it's taking too much. Okay, yeah, so the reason, what's that?
On page 3.
We're on page 3?
Yeah.
Yeah. I know we're on page 3, right? We're still on page 3 and we have 20 pages to go. Well, should I proceed or? So, look at this. Okay, try to name that, right?
Okay. Three methyl. Heptadiol.
Is that 4-methyl
3-methyl.
heptane?
Okay, what do you guys say?
3-methyl.
3-methyl heptadiol. Heptane diol.
Is it 3 or 4?
3.
Exactly. So you have to start with the one it's closer to, right? So, but we still don't say 1, let's see, 4, 5, 6, 7. We're not going to say 1, 7 dial because it's either way going to be terminal at the end, right? So when you're practicing now, which is something I do, right? Even though we've given you this, I can just change this to that. So what other concept have we introduced? Stereochemistry. So you have to think broadly when you're studying. Okay? All right. Yeah. Huh? Figure that out. Okay. So you don't have those in the book, but yeah, which is why we're thinking of switching from McMurray actually, because it's so limited in the examples it's giving you guys. So we have a bunch of books we're considering. We can't decide on one, right? Plain is there, Cathy is there. There's so many, so we don't know. There's another one, Loudon. So we're still thinking, but McMurray, yeah. It's simple, but it's oversimplified the thing. So when you use it to study and then we bring the exam to you, it's like we're teaching you something that we didn't actually teach you, but we've actually taught you. It's just that you don't have enough examples to work with, right? So I can maybe I should even write mine. We'll see. All right. I'm actually thinking about that. Well, it's not going to be like in the form of the book like that. It's something like a guide, right? So we'll see. You won't need it. Don't worry. People after you will need it. I'm gathering the experience now. Been teaching for how many years now? Like what? Wow, it's been a while. All right. So, okay. So there are some common ketones named that you're used to by now. You've used them in the lab. Acetone, right? Common solvent, cleaning solvent. Benzophenone, you use a Grignard, right? Acetophenone is a family of benzophenone, but it has this acetyl group, so that's why it's called acetophenone. Okay, so just get used to those. All right. Okay. So here. Oh, by the way, naming the ketone too. There's an example there in the book on F. I'm not going to name that, so you guys should work on that, right? In the book, it gave the answer as C's, but that's incorrect. That's partially correct. It's incorrect. That's why I give partial credit when it comes to stereochemistry, even though I don't tell you I give partial credit actually. So I'll give you credit for indicating the stereochemistry and giving the name. But when you're doing this on OWL, it doesn't give you that option. It's either you're right or you're wrong, correct? But people don't see it as partial credit though, so I don't give partial credit yet.
I agree with you, but how come the book overlooked like such a big concept?
Yeah, so stereochemistry is a different field, a whole chemistry on its own that some chemists think, well, don't let me overwhelm the students with it now. That is the same mistake that was made in the 1950s, 60s when that drug was sold, right, in racemic form because it was, Kaya Center, who cares, right? And then it led to a lot of nasty things. Baby born being deformed, without limbs, without legs, without eyes, without, right? Just because of one single chiral center. Okay, so they overlooked it for a long period of time. So it's a branch of chemistry on its own. Okay, so he just felt, who cares? Let's use cis and trans. Okay. And believe it or not, a lot of other chemists that are not in the field still don't take it seriously when they're teaching it. Right? Some professors will just give you cis and trans, that's fine. Go ahead. But I react to it. It's like an allergy to me when I see it. If you do that, it's like, no, that's wrong. Okay, because, yeah. All right. So it's partially correct, but not completely correct. Again, we can demonstrate that by just switching the stereochemistry, right? And then you see that they're different, even though they are Cs. Okay. All right. So there are other functional groups that we've not talked about, like carboxylic acid, esters. We've not talked about naming them. Okay. If those functional groups are present in the structure, your ketone functional group now becomes a substituent. All right, and it will be named as an oxo. So whenever you see the name of any compound and it has oxo in it, that means there's a carbonyl at that position. So for this example here, you have 3 oxo. That means your methyl group, your ketone group is at position number 3 from the ester group. So that's why it's methyl 3-oxo-hexanoate. Noate represents the naming ending for esters. I guess because you have them in foods a lot, so that's why we use A. You eat them, right? So yeah, right? So it's not you made them in the lab. They're nice smelling, right? I think the chem major synthesized esters, so they're nice smelling. Pineapple, apple, banana smells. You can't just taste them, but you can smell them, right? So it makes you feel good. All right. So whenever you have that group present in a higher functional group, it becomes oxo. But there's going to be few examples for that because we've not talked about it. So we're going to stop there today. All right. You have a nice weekend. I'll see you on Monday. Those of you that have not picked up your exam, I have them here. Yeah, I was trying to upload. I was trying